It is fall 2023. This is Measurements and Automation, Project 5. This is our first project utilizing LabView. For this project, we were tasked with making 3 different designs, each of which uses numeric operators, Boolean operators, and summa, numeric and Boolean displays, as well as numeric functions, Boolean functions, and for loops. So we'll start here with our design 1. This simply is a simple calculator that computes a plus b plus c, a minus b minus c, a times b times c, and a divided by b divided by c. And the value of a, b, and c are controlled with these 3 numeric controls here. So as you can see, the value of them change as the inputs change. And if you want to pause the video and check the math, you can, but math is defined right here on the block diagram. So as you can see, we have our A, B, and C. Write it down. Had to make it look pretty for me. And here we have 2 plus numeric functions, 2 minus, 2 times, and 2 divided. For the minus and the plus and the times, the order does not matter, but for the division, it does matter. And then all of the outputs are defined there on the right side. Moving on to the second task for design 2. We have a similar thing, but it's actually not that similar. We have a 4 input and, or, NAND, and XOR gate. You can see that on the back panel, or on the block diagram here, where you can see input values, and they go into the necessary 4 input gates. For the AND gate, the OR gate, and the XOR gate, you can simply cascade these values in. But for the NAND gate, you have to do a little trickery here. So you take the first row, NAND gate, A and B and C, kind of how you would, or A and B and C and D, the way you would expect. Then you have to take the output and plug both of them into the inputs of another NAND gate, and then take that output. I'm not going to go into why that works, but that is what's required to make the NAND gate work properly for multiple inputs, more than 2 inputs. So here you can see, we'll go through here. So we're at 0, 0, 0, 0, 0, 0, 0, 1. And we're just going to go through all states. And you can see it is displaying the proper value for each of these states. And you can see there the NAND gate, or the AND gate, only came on when all 4 Boolean switches, Boolean buttons are high, which is what you would expect for an AND gate. Now the final design down here, you can see sorry, let me scroll down anymore. You can see the design number 3 for this one, a simple calculator that takes a integer value in and computes the factorial of it. Now it's worth noting that a factorial is only defined for values equal to or greater than 0. So all these values here, you're getting 1, but they're actually undefined. And then in addition, so the lower bound is 0, and the upper bound for this system is actually 13. You can see as I go past 12 here, these numbers aren't increasing the way you'd expect them to. That is because this is a 32-bit version of LabView. So the max positive integer is about 2.1 billion, and 13 factorial exceeds that by about 4 billion. So you can see that here. So as we go from here, 12, and this is 479 million. If you multiply that by 13, you should get something much greater than 1.9 billion. But due to overflow, you do not. And that was not addressed in this design. So for the block diagram for that, we have a simple for loop here, taking the input, the input. In addition, this for loop has the shift register active. So for the lower bound, it has a 1 as an initial value, and then the output goes into the numeric indicator here, and in between here, all we're doing is we're taking the initial value 1, multiplying that by I incremented, and then outputting it. So, of course, each time this goes up, so at 1, we're simply doing 1 times 1. That checks out. Here, we're doing 1 times 2. That checks out. Here, we're doing 1 times 2 times 3. And again, that checks out as well. So that continues up again until that upper bound. So that is our first project using LabView. There will be more to come, likely much more complex than this, but thank you for watching.